And thank you for inviting me, Raphael. So yes, we're here to talk today about our project, which is called FeNN DMA. Um, and I'm going to give a little bit of background about spiking neural networks and FPGAs. And then we're going to switch over to my colleague Zainab, who's going to talk in some more detail about the hardware that we've developed. Before switching back to me to talk about the software, and then very briefly about the results, because I realized for this audience, some kind of results of spiking neural networks aren't necessarily that relevant. And then we're going to talk about future work, which is hopefully exciting for everyone. If you're interested in this project, I've got the link at the bottom of the slide as to our most recent archive, and this has got this is relatively up to date, and this contains most of the stuff we're going to be talking about today. So some background: spiking neural networks, what are they? So I hope at this point in 2026, we all know what artificial neural networks are. So spiking neural networks are kind of a biologically inspired sort of recurrent neural network. And the key difference is that rather than the neurons having analog activations, they have binary spiking activations. So the spiking neurons integrate these weighted binary spiking inputs, and then they emit spikes of their own. So this is inspired by biology because in most parts of the brain, this is how biological neurons work. And the key thing is that time is key to the encoding. All these spikes are exactly the same, so the only way they encode information is in the time that they occur. And this means that these networks are well suited to temporal and spatial temporal tasks. Like they're not really very sensible for classifying images because there's no time dimension in images. So you'd need to add a time dimension, and then you've lost a lot of efficiency before you begin. But if you've heard one thing about spiking neural networks, you've probably heard that they're efficient. And the efficiency savings come in from two main places. So one is the sparse communications. In modern electronics, like in the brain, like the cost of communication across the chip or between chips is by far the largest energy sink. So because these spikes are fairly infrequent and they don't have any value, they're just ones or zeros, there's a significant saving in communication by communicating spikes rather than continuous analog values. And also because the spikes are binary, when you weight them, you're not really multiplying, like you're just selecting weights and adding them together. So if there's no spike, then you don't select any weight, so you have nothing to do. And if you've got one spike, then you add the weights. So there's a saving here from switching from multiplication to addition and doing less of it because you only ever need to add when there's a spike. So in our group at Sussex, we've been working on accelerating spiking networks on GPUs for quite a long time. I think our first paper, my colleague Thomas Novotny, was back in 2010 on one of the first CUDA GPUs. And whatever it is now, 16 years later, we have a fairly mature library for simulating spiking networks and GPUs. Just go to our homepage, genteam.github.io if you're interested. But in short, we've got two main conclusions from all these years of work. So by exploiting the sparsity that we've talked about, so the sparsity of the spikes, spiking neural networks can be trained much faster than RNNs on GPUs. And for us, this is really exciting. Like this is kind of saving and training time and memory, not just inference as training. So here on the left, we've got some slides from a recent paper, and basically the dotted lines are training spiking neural networks as if they were normal RNNs using PyTorch, and the solid lines are using our tools. And you can see that both GPU memory on the left and training time both grow much more quickly if you ignore the sparsity and treat spiking neural networks as RNNs. So there's some real savings to be made here, even on GPUs. And the other thing that's where currently GPUs are looking very attractive is for kind of large-scale computational neuroscience. So in this kind of the main spiking neural networks being used to model the brain rather than to do AI. We've got a recent paper here where we're comparing a single very high-end GPU to a whole cluster of CPUs, like a 32-node cluster. I found that this very large model, which had like 24 million neurons and many billions of connections between them, on the single high-end GPU, it was faster than this 32-node cluster. In fact, the only thing that was faster than it was a cluster of GPUs. So that even so, GPUs may not seem the most suitable piece of hardware to exploit these networks, but they're not. But there's still some benefits to be had. So what does the actual computation look like that you're simulating in a spiky neural network? So there's other ways of expressing this, but basically you have a time-driven component where you're simulating the neurons. So you have some number of state variables. In this case, you've got a V and an I state variable. So the V is the state variable, the I is the input. And you perform some maths on the state variables. And there's some kind of condition that you test on the state variables, which emits a spike. And then these spikes are accumulated using some code like the code on the right. You basically loop through the spikes and you add the weights together. So this you don't need to really grasp the full detail of this, but the key point is that it's very memory bound. So we've got four memory instructions in this time-driven bit. We've only got 2 arithmetic instructions. So the arithmetic intensity of this kernel is less than 1 op per word. And this is an even more extreme case. Like in this is written in such a way that it looks better than it is, but you've again got less than 1 op per word arithmetic intensity. So very low, especially when you consider like GPU designs. They're focused on AI acceleration these days, and GPUs and TPUs and lots of other accelerators are focused on this. And here the main computation is matrix multiplication. And this has got a very high arithmetic intensity because you load kind of whole tiles of matrix into memory. And then because of the nature of matrix multiplication, you could then perform a large number of operations on the same data. And this means that these latest high-end GPUs, they've got a kind of arithmetic intensity of like 100 flops per word, which means you need to do 100 math flops on each word to fully occupy the device. And the problem is, as we found before, our spiky neural networks are down here. So spiky networks are very memory bound on GPUs. They work quite well because GPUs have got lots of memory bandwidth, but they're very memory bound. So in some recent benchmarking, we found that on a modern GPU, some of these kernels were hitting 90% of the memory throughput, but only 17% of the compute. And also because these things are iterative, like RNNs, it requires many kernel launches, and this induces latency on a GPU. So they're not ideal. So how can we improve this? Well, this is all kind of basic computer architecture stuff, really. We can reduce the memory bandwidth requirements. So we can use sparsity. So we're already using spatial sparsity by using spikes. Sorry, using temporal sparsity because we're using spikes. We can also add an element of spatial sparsity, so we can have like sparse connectivity. And this is something that we're going to talk about in a little bit. And we can also use lower precision types. So by reducing the width of your data types, you reduce the memory bandwidth. Alternatively, you can go the kind of brute force approach and just increase the external memory bandwidth. But the GPUs are pretty much on the memory bandwidth scaling as hard as they can, right? They're on high bandwidth memory 3 or whatever at this point. It's hard to get very much more external memory bandwidth. One thing you can do is you can kind of sacrifice some of the arithmetic logic units and tensor cores that a GPU has and replace them with more local memory. So if you have lots of local memory, you can move some of the data into local memory, so it's permanently resident there rather than just being cached, and operate on it there. So then you don't have to use external memory bandwidth for everything. And some of you might have heard of neuromorphic hardware. And so these are basically systems designed specifically for spiky neural networks. There are analog neuromorphic chips, which are a whole other cool thing that isn't really in scope today. But basically, digital neuromorphic chips are not magic at all. They follow exactly the approach I said on the last slides. They typically remove external memory entirely and add large amounts of on-chip memory, and they take advantage of all the types of sparsity, and they use reduced precision types. And this results in massively reduced power. So these 2 top systems made by a Swiss company called SNNs, and these are both kind of extreme edge neuromorphic chips. So this one on the left, the spec, has got a camera built in, and the one on the right has got generic sensor interfaces for kind of lower dimensional stuff. So in this kind of space, neuromorphic chips are clearly the winning way to deploy spiky neural networks. But if we're thinking about kind of bigger systems for either development or training or just kind of running bigger inference models, these systems lose a lot of the nice things about GPUs. They don't tend to be programmable, at least not fully programmable. And more practically, they're not in the right form factor for a developer, right? You want something like a GPU that you can stick into your server. It's sitting there in your memory space, and you can copy data to it really fast through PCI Express and stream your data set in, all this type of stuff. And this is kind of a bigger problem with ease of integration. So if you feel like you have a lot of money, you can buy one of these Intel Huller point neuromorphic systems, but it's kind of a big standalone thing of a lot of neuromorphic cores that sits on the network. So it doesn't really act like a GPU server. You have to totally rethink all of your processes to use something like this. So we strongly believe that for spiky neural networks to be adopted more widely, we need accelerators that are like easy to use and to integrate into standard systems. So they're easy to program and they're kind of more standard looking. So what do we do? Well, how can we make one of these? So we've already said that GPUs are good because they've got high external memory bandwidth, but they're bad because they've got not enough local memory and they've, if anything, got too much compute power. Obviously, if we had lots of money, then we can translate that money into expensive memory controller IPs, massive area for SRAM, and build an ASIC. But the problem is we're in academia, so we have to think of alternatives. And I think in this context, FPGAs are a really interesting idea because the typical high-end FPGAs come with high-end memory controllers, so kind of high bandwidth memory too. They come with large local memories, and they have a moderate amount of compute power. So the reason they haven't been particularly popular in mainstream artificial neural networks is because they can't really compete with GPUs. But in spiky neural networks, the compute power isn't so important. And the nice thing for me as a kind of high level hardware person, I guess, is that someone else has done the job of turning these things into usable systems. So we're looking at Xilinx systems, Xilinx/AMD systems for no particular reason. But here we've got kind of two ends of the spectrum. So we've got this thing called a Korea KV260, which is a kind of thing you might stick on a robot or in a sort of mid-size edge system. It's got 4 gig of DDR4 memory, which is pretty fast memory technology. It's got almost 3 meg of on-chip memory, and it takes burns about 15 watts of power. But this thing's running Linux, and it acts much like an NVIDIA Jetson, but with an FPGA rather than a GPU, which is really nice. And then at the high end, you've got something like this Alveo card, which has got 16 gig of second generation high bandwidth memory and over 40 meg of on-chip memory, which is much more than you get on essentially the cache on our high-end GPU. And it's quite power hungry, but not as power hungry as a GPU. So these are the kind of the sort of spectrum of devices that we're kind of thinking of deploying these things to. And what are we actually doing? What do we actually want to build? Well, there's lots of fixed function FPGA, lots of fixed function spiky neural network accelerators on FPGA, and these are potentially a good match for deploying spiky neural networks in some kind of low volume context. But we want to build something flexible for researchers. Like we said, we want something that's easy to use. And this means that if you need to resynthesize your design every time you change your model, it's not really practical. And if you having to use, and also just having to use the FPGA CAD tools is a very high barrier to entry. I can barely do this. I rely on Zainab. So the other interesting point is that because spiky neural networks aren't compute bound, if all our algorithms take a few clock cycles more because they're programmable, it doesn't necessarily matter very much. And this is not an entirely novel idea. There's some older papers here where people were having these same thoughts about FPGA. And obviously we want to use RISC-V because it solves a lot of the annoying problems of having to make your own basic core and figure out a nice instruction set. And you don't have to be concerned about licensing issues. It's really, we're big fans. So what kind of programmable system are we going to build? Well, we're going to build a SIMD system. So as I'm sure all of you know, in the SIMD system, your operations look much like normal operations in a RISC CPU. So you might have an add operation that reads two vector operands and writes back the sum to a destination register. A SIMD version would be exactly the same, but the registers would be much wider, and you'd be adding together multiple values at once. So this is interesting in the context of FPGA, and generally in the context of accelerating spiky neural networks, because you're kind of amortizing the cost of the programmability across multiple lanes. You've only got one control flow, but your control flow is bringing with it multiple computing multiple things in parallel. So the cost of the kind of basic core is amortized across potentially a very wide accelerator. And also the high parallelism helps counteract the low clock speed of FPGA. I'm aware there's some RISC-V based spiking neural networks accelerators built for ASIC that have much less parallelism than we're going to talk about in the system that we built, but they can also run at a much higher clock speed. So on FPGA, we kind of want to be wide and slow, I guess. And again, this isn't a particularly novel idea. Back in the 2010s, some people at University of British Columbia were making a whole bunch of vector processors using FPGA. So that's the kind of basic structure of what we're going to build. I'm now going to hand over to Zainab to talk about the details. If I can get back to this.
Hello everyone, is my screen visible?
Yeah.
Yeah.
I think you need to put in presentation mode now. Yeah.
Yeah. Hi everyone, I'm Zainab Azaz and I'm going to explain the hardware implementation of FeNN DMA. This FeNN DMA is built on Crea KV260 board, which has an AMD Xilinx UltraScale Plus architecture. So this architecture has two basic building blocks, the processing system and the programmable logic. So the processing system contains a hardened component that cannot be reconfigured and that can be used as they are. And it contains external memory also. And the processor is used to manage the operating system and handle high-level control. And whatever we design on the programmable logic, we can control that using this ARM processor by running software that's relevant to run on this programmable logic hardware design. So what is programmable logic? It's a bare fabric on which you can custom design any hardware, almost all kind of hardwares, digital hardware, and even analog hardware. So using lookup tables, LUTs, registers, block RAMs, digital signal processing units, and input outputs. So these PS and PL are connected using AXI, which is a standard bus system used by ARM, and also called Advanced Extensible Interface. And this is a high performance bus and can deliver at a throughput of around 4.9 Gbps per interface. So knowing the capacity and type of memory for building an AI accelerator on FPGA is critical because the performance, efficiency, and feasibility of the design is almost entirely dependent on how well the accelerator manages data movement. So we have two kinds of memories on this Zinc UltraScale architecture. The external memory, as we just talked about in the previous slide, which was on the PS side, and the internal memory, which is built on the programmable logic. So external memory is a high capacity storage. It's a double data rate RAM and provides very high bandwidth. And internal memory is high speed. How it is high speed? Because it's built, these are the primitives that are built on the programmable logic, and whatever custom hardware you design on a programmable logic, you can access these memories which are nearby. So there is very high speed when you are using these memories on the programmable logic. And the drawback with the external memory is that you need AXI buses to have the data transfer, so it is a bit slow. So we utilized all these memories in FeNN DMA. Another important unit in FPGA is a DSP block, a digital signal processing block. It is a hardened unit, means you cannot reconfigure it. You have to reuse it as is, but it's written that it's 2718 input width, although it's very flexible, and you can have an 8x8 multiplier, 8+8 adder, 18+10, 18 multiplied by 10, and all sort of calculations you can easily perform on these DSP blocks. And these blocks are highly optimized for latency and performance. And they also have one cycle latency, so like BRAM and UltraRAMs. This is the complete system on chip design of FeNN DMA. FEN DMA is essentially FEN with the DMA. So initially our first design was FEN, FPGA Enhanced Neural Networks, which used the RISC-V processor, the vector processor, ARM core, but did not use the DMA controller. But now in the FEN DMA, we have designed a custom DMA controller. So then it's called FEN DMA. So I can explain it starting from the left side, that this ARM core is the processing system that throws the software on the programmable logic side. So whatever on the right side of AXI interconnect you can see is the programmable hardware, is built on the programmable hardware, on the programmable logic, and is custom designed. And then this DDR is also on the PS side. So when the ARM core send instructions means RISC-V instructions from the interconnect, through the interconnect to the instruction memory, this CV32E40X, which is a RISC-V core, fetches those instructions, execute the instruction if it's a scalar instruction, stores the result on the scalar data memory. These results can be shared by the ARM processor and stored on the DDR, the external memory. Also, if the instruction is a vector instruction, then it's offloaded to the vector processor, and the results can be stored to the URAM, which is a vector data memory. And from there also, it can be written back to the DDR through the arbiter. So this is how FEN DMA works. And you can see that there are different kinds of AXI buses as per the arrow notations, and the blue arrow and the purple arrows are instructions. The blue arrows represent control signals. The red arrows represent data, and green represents the connection between RISC-V processor and the coprocessor. So I'm going to explain in detail all these units, all these building blocks of FEN DMA. Firstly, the RISC-V processor. We used CV32EX, E40X core developed by Open Hardware Group and ETH Zurich. It's a 32-bit open source in-order RISC-V processor, and we use RV32I instruction with multiplication and bit manipulation extensions. And it's a 4-stage pipeline core. So you can see that instruction memory and scalar data memory are used, are BRAMs, the block RAMs. So originally, this core was designed for ASIC, application-specific integrated circuits. So these memories were accessed using an OBI interface and were suitable for ASIC. But we wanted it to be optimized on FPGA, so we changed and we optimized these fetch unit and load store unit to synchronize them with the modern BRAMs of FPGAs. Now, this is the vector processor. This is completely designed by us, and it is a coprocessor to the RISC-V processor. So it is a 3-stage pipeline and 32-lane processor. So lanes are the parts of the vector processor. So if there are 32 lanes, then 32 operations are executed simultaneously by the processor. So this is how lanes work in a vector or SIMD processor. So the vector width over here is 512 bits. That means the full vector is 512, and there are 32 lanes. So each lane has a 16-bit operand on which you can perform any operation. So there are 32 lanes that work parallelly and are executed parallelly. So the register file, of course, is 32 deep and 512-bit wide, having 2 read ports and 1 write port. And you can see that the VEC does not have any fetch unit. It looks like a processor, but there's no fetch. So it's actually, we have used a system Verilog construct that was available with the CV32E40X RISC-V core. And this construct is an interface that helped to encapsulate communication between these two processors. So the issue construct helps to offload the instruction from CV32 RISC-V core to the VEC. The instruction is then decoded in the vector decoder and register file. It takes the data from there like usually the processors do. And the seed and RNG registers are useful for the stochastic rounding, which I'll be explaining later. And then the instruction goes to the forwarding multiplexer. I want to recall that we use forwarding multiplexer for resolving the data hazards. And those hazards occur when one instruction requires the result of the previous instruction. And that result is obviously not in the register file because of the pipelining. So this forwarding multiplexer transfers those the previous instruction's result from their current location to the location where it's required by the next instruction. So this is how forwarding multiplexers work in vector processor. Then the instruction goes to the IDX, that means instruction decode and execute pipeline, and then it enters the vector arithmetic and logic unit. And this unit contains lots of calculation, lots of units that are required for vector calculation, which has a width of 512-bit. So adders, multipliers, and all those comparators are there in the vector ALU, and the width of everything is 512-bit. And then the execution goes to execute and write back, where the results are written back to the register file, or they are written to the memory, the vector data memory. Also, for some instructions, we require data to be fetched from the data memory, vector data memory, and we do have a lane local memory suitable for spiking neural networks. So I'll tell this in the later slide, but I would like to explain what is commit. Commit is again an interface that decides whether the instruction is good, it should be executed. Otherwise, if it's not, then it should be killed. And the result interface is used to transfer the scalar results back to the CV register, CV32 register file. So this was our vector processor, and I need to know, you should know that what are the memories and what are they made up of. So instruction memory and scalar data memory are any memory of the coprocessor in a RISC-V, in a Harvard architecture. So instruction memory in our case holds RISC-V instruction, and scalar data memory holds addresses and spikes. Also, the vector data memory, which is entirely built using URAMs. URAMs are wider memories having 72-bit of width. So URAMs are used in this memory and are used to store neuron state variables like voltage and current in spiking neural networks. We have finally the lane local memory. As you can see, there are 32 partitions. So each of these partitions represent a single block RAM having 18 kilobit of capacity, and this block RAM represents one lane. So to support delays and sparse connectivity, we require indexed closed instructions, and therefore each lane requires an independent address. So every of these memory is for one lane. So 32 single block RAMs for 32 lanes, and which has helped us quite a lot for this sparse connectivity of SNNs. So the ARM core, as you remember the SoC diagram I showed you. So on the left-hand side, we have the ARM core and the DDR. So this ARM core is, I'll explain them in detail, of course. So quad-core ARM Cortex, it's a quad-core ARM Cortex processor, which is available on the Zinc Ultra scale. And then it's programmed by our SNN FeNN library on Ubuntu Linux. So Ubuntu is installed on this, and then we run the code using FeNN. So the code transfers a lot of signals on the programmable logic side through the AXI interconnect. So these three types of signals are instructions of the RISC-V processor, the controlling of DMA, control signals, and the execution of transfer of data from DDR to the DMA and from the DMA to the DDR. And it can be noted that DDR stores the weights of the SNN application. So the DMA controller in detail, I would like to explain. So as I told you earlier that we custom designed this DMA, but we use the AMD AXI data mover IP, which is already available in AMD. So this is ready-made, and it's for high throughput data transfers. And this data mover IP, it is similar to a DMA, AXI DMA available in Vivado, but Vivado is the tool on which we design the programmable logic. So it is similar to the AXI data mover IP, but it's controllable by hardware and have much higher performance than the other IP. So this controller we designed, and we created a finite state machine in this, which starts when ARM core commands it to send an instruction so that data mover starts the communication between DDR and vector data memory. And the data mover also sends status to the controller, whether there is an error or the communication is going nicely. And what is arbiter? Arbiter is used to arbitrate between the memory mapped and stream, memory mapped to stream, and stream to memory mapped. So what is memory mapped to stream? It's communication from DDR to URAM. Because DDR is memory mapped, you access everything on it through the address in the memory. That's why it's called memory mapped. So from here and to stream, Why URAM represents a stream? Because communication, the transfer of data is taking place through AXI stream protocol. So that's why a DDR to vector data memory is memory mapped to stream transfer, while a stream to memory mapped is transfer from data memory to the DDR. So this is how it's happening. Now, a DMA controller, as I just told you, is not only working based on ARM core, but first let me focus your attention towards this table on the left-hand side. You can see there are 10 registers. These are the registers we build inside the controller. FSM, the final state machine. So these registers, how do they work? This is MM2S source address. So you know that MM2S is transformed from DDR to data memory. So DDR is the source for MM2S. So this 32-bit source address is the address where the data is residing. And this destination address, MM2S destination address, represents the address where the data would go and be transferred to the URAM. MM2S count represents the number of bytes to be copied. MM2S status tells that that code or transfer has some error, or the transfer is running nicely. And MM2S control is the register. In its lowest bit, we write 1. So the ARM core in this dotted arrow control signal writes 1 to the lowest bit of the MM2S control, which makes FSM perform send command to data mover, which allows the MM2S transaction. Similarly, for S2MM, this happens so that when S2MM control is written 1 by the ARM core, the communication from the transfer of data starts from vector data memory to the DDR. So this way these registers work. But there's another way, is the CV32E40X core, and we use its control and status registers to do this work. We send instruction in the instruction memory, and then the CSR instruction makes this happen and writes on the control register to perform the same task. So the addresses of the CSR that we coded are BC0, BC1, and written over here. So we can initiate using ARM core, the transaction, the DMA process, or using the CSRs, both ways. So why we are using RISC-V processor for the SNN acceleration? Because RISC-V processor enable us to create custom instructions tailored to our need. In SNN, there are at various places we require for larger models, we require lots of data transfer and generation of random numbers and stochastic rounding to be performed at various units. So any single processor, any already built processor will not efficiently do, obviously. So we need a processor who works on the instructions that we tailor, that we tell them to do in this way or that way. So RISC-V allowed us to make our own vector processor as a coprocessor, and we built a number of vector tailored instructions which are tailored to the SNN. So the 32-bit instruction format for our vector processor is what is prescribed by RISC-V for the coprocessor, and the opcode you can see, and then RD is the destination register. So this is the instruction vmul, means vector multiply. You do multiplication of V2 and V4 registers in the register file and save it to V6, which is a destination register. So this is RD destination register. This funct represents vmul or vadd and such things. And then RS1 is the source register, that's 4. And RS2 is another source register, that's 2. And 4 multiplied by 2 would be saved in RD. And the funct represents some of the specs that if you have this bit is saturation, if this bit is 1, the 31st bit of the instruction, if this is 1, you would saturate the result after multiplication, otherwise not. The next 2 bits are for rounding, because we have 3 kinds of rounding in vector processor. So these 2 represents which kind of rounding you need to opt for. Then you have the next 4 bits are for shifting. Later I'll show why we are shifting, but this like 13. So the result of the vector multiplication should be shifted by 13. This is shown by that. So this is how 32-bit instruction format for our vector processor works. So these are instructions that we made, and vector arithmetic instructions performing addition, subtraction, multiplication, vector immediate instruction, so shifting and all performed on immediate, vector test instruction that test the equality or not equality of the vectors, vector fill and extract, you need to fill the register file by some constant, so vector fill, Vector extract, you need to extract some constant, and then from the vector register file to be used in another process. So this is for that. And then vector select works quite like conditional operator of C. Then vector load is for loading the data from vector memory, from lane local memory, from the seed registers. I'll explain what is seed registers, but it's used for stochastic rounding. And then vector store instructions are for storing to the vector memory, storing to the lane local memory. And these special instructions have been very useful. Like this instruction, vrng, calls on RNG, random number generator, to generate random numbers. And then vand add, it performs addition and ANDing all in one cycle, which was not possible by any another already available instruction. So these instructions have helped us to generate, to run our SNNs efficiently in fewer number of cycles compared to any other way. So I would also like to explain you the random number generator, because why we require an RNG, because for any SNN, stochastic rounding and random numbers are very important for the complex numbers, and for the complex functions we need the random number generator. So we used already available Zoro-Shiro generator from Bachmann and Vigna, and it's extremely hardware friendly, just made of a few XOR gates and AND gates. And if we would have to do this random number generation using standard RISC-V, we would need to have 32-bit and to read those 32-bit and write 48-bit per cycle, which would require extra register file ports, and that would always obviously create a mess in the CV32 or the RISC-V processor. So we designed these two special processor for the random number generation, as was written in the vector processor diagram, the seed and RNG. So we require actually 32-bit of seed per lane for stochastic rounding above the standard operation. So these are registers which were built using distributed memory in the vector processor for performing the random number generation. Finally, I would like to explain multiplication that we are doing. It's sort of like a MAC. So you can see that what we are doing this process, then multiplying and adding a random number and then shifting by n. So you can map R over here to the right side with C. So this is a DSP block that I discussed initially. It multiplies two numbers and then adds C with it. So because we have three kinds of rounding in our required in our SNN application, round to zero, round to nearest, and stochastic rounding. So you can see that there's a mux that selects which kind of rounding. So if it's RZ, it's round to zero, and it makes C equal to 0. And if it's I'll talk firstly Rn, that's round to nearest, so it's like 0.5. So we send 0.5 and then it rounds to nearest. And in stochastic rounding, we take the input from the random number generator, and then it sends the random number, 16-bit random number, which goes here and gets added for the stochastic rounding. And why do we need a shifter? Because as you just saw that in a vector instruction, when the results are stored, they're stored back to the register file, which has an operand of 16-bit only. So each lane is 16-bit. So we need, because the output of multiplication of 16 bits and 16-bit is 32-bit, we need to shift it by 16-bit to make it 16-bit again. So this is how the details, how the VEC works internally. More to Jamie.
Thanks, Zainab. Let's get my slides back. So, like with all good hardware projects, the software is also pretty important. So we started, so in our initial, one second, I'll hide this. In our initial paper, we were just kind of exploring the algorithms. So we built a kind of initial tool chain to program this thing purely in assembly language. So we tried to use as much open source software as possible in this process to save us time. So we started with this XBIAC JIT assembler, which basically lets you write RISC-V assembly language fairly conveniently from a C++ application, which is exactly what we needed. And then while Zainab was building the hardware, we wanted to have a simulator. So we started with this slightly random single file RISC-V implementation from the internet, this thing called Nido PC5. We kind of refactored that a bit and added added a instruction set simulator for the vector instruction set that Zainab's described, and also a simulated DMA controller, so we could do use the CSR instructions Zainab talked about. So this let us build sort of initial software, assembly language, and test it on a standard PC. But then we wanted to run this on a real Kriya. So we had, as Zainab has said, the Kriya is running Ubuntu. And here we use some kind of open source driver interface to communicate with this. So we use UAO, which is kind of a Linux standard for user space communication with memory mapped hardware. So this is what we use to like write to the DMA controller registers, all that type of stuff. And also we use this open source driver called UDMA buff, which does the contiguous memory allocation you need to use the DMA controller. And we wrap this all up with a kind of C++ device interface. So using this, we kind of wrote the first sort of test spiky neural networks for FEN. But we are really interested in making something usable, and writing spiky neural networks in assembly language doesn't sound particularly usable. So we then sort of started building this backend. So we wanted, so in our gen software, which I talked about earlier for simulating spiky neural networks and GPUs, we have this kind of C-like language that's used for specifying neuron models and other programmable bits. So we started by we started with this, and this produces an abstract syntax tree of these kind of programmable neuron models. So we built a very simple compiler to the vector instruction set from this. So we allocate registers very conservatively. So we allocate registers very conservatively. So it's quite a simple compiler at this point. But combined with some sort of simple memory allocators for the various types of memory that Zainab talked about, and a runtime that kind of handles starting and stopping FEN using the memory map registers or this type of stuff, we now had something that we could program in a high-level language. And on top of this, we built a front end, where you can describe your models in a relatively high-level way. So you have these things called processes that describe things that run on FEN. You've got variables that are basically arrays, and event containers that handle transmitting spikes around. So with all these three layers in place, you could now write spiky neural network models in a fairly high-level way using C++. But based on our experience with Gen, people don't really like writing C++ very much more than they like writing assembly language. So we finally built this layer called Python on top of this, which lets us program the whole system in Python and totally abstracts away if you're running on the real device or the simulator. This is only kind of a vertical slice of what this toolchain is going to look like. We're going to iterate on it a lot more, but for now it seems to work quite nicely. So what does this actually look like? So this is what neuron, if we think back to the first slide, looks like written in this way. So if you use PyTorch, you should be relatively familiar with the kind of structure of wrapping up these modules in a class. So here we have this lift neuron, which stands for leaky, integrate, and fire. And this is basically the model we showed in the second slide. So you can see there's some state variables, and there's this process for implementing the neuron written in fairly straightforward looking C-like code in the string. And the other key thing here is we've got these fixed point types. So as Zainab described, FEN's multipliers support native fixed point multiplication. So all the multiplications can be followed by a shift, and they can support saturation. So here we're saying that the V variable has 9 fractional bits and it has saturation. So the additions saturate, and the decay variable has 15 fractional bits and again saturates. And this run through our compiler ends up looking something like this, which you should recognize from Zainab's slide about the instruction set. So you can see here that you've got some immediates being loaded. So these are the kind of the constant parameters. We're loading some state variables, doing a little bit of maths, and writing back the state variables. And here we're using this select mechanism to determine if to update the voltage based on the spike or not. So when we've got this, we can then kind of build simple models. So here we're looking at a simple kind of multi-layer perceptron of spiking neurons. So here we put some inputs in this event container, and we pass these to a layer of these lift neurons in the hidden layer, and we read off the output in this non-spiking output layer. And they're connected together with these linear layers, much like PyTorch. And again, you can see we've got these fixed point types here of the weights. So this is kind of what it looks like to program FeN at the moment. And so under the hood, I guess the most interesting thing that kind of brings together all the components as we have described is how we actually do this operation in the right. So how we implement this summation of weights efficiently with the weights in DRAM. So in this situation, we have in BRAM we have bit vectors of spikes. So here you can see there's a 32-bit RISC-V register, and you can see that the second, fourth, and fifth bit are set here. And you've also got this weight matrix sitting in DRAM. So the way we process this is we first of all prefetch the row of weights associated with the first spike into a URAM buffer. And this incurs some memory latency, but this is the only memory latency you see in our algorithm. So because next what you do is you simultaneously, you start fetching the next row of weights, and at the same time you start processing the row that you got before. So this consists of just like adding them to this I variable. So we then keep doing this. So we're always double buffering our fetching and our summing of weights, and this works out very nicely. So it ends up the cost of processing one of these like rows of weights is enough to hide all the latency of fetching the DMA and the time it takes to actually transfer the data. So using the DRAM doesn't actually have very much overhead, which is kind of the key of these memory bound low arithmetic intensity algorithms. So that was just a weight matrix, but connectivity in the brain is very sparse, and this is kind of related to pruning in ANNs. So if we can have sparse connectivity, we can prune networks and get them to run save memory and save compute. And the nice thing is that unlike with matrix multiplication, where multiplying by a sparse matrix is really expensive, propagating spikes with a sparse matrix is kind of easy. But the problem is it involves this scatter-gather memory access pattern that's not very GPU friendly. Like it's sort of handled in the L2 cache up to a certain point, but when you run out of L2 cache, it becomes very, very slow. But on FeN, this isn't a problem because we have these lane local memories, which, as Zainab said, mean that you can have independent index loads in each lane. And the way we map this sparse connectivity problem to this is that in the weight matrix, we split the 16-bit weights into a lower precision weight and an index. And this index is basically pointing to a position in this lane local memory. So the weights are then sorted so that all the weights which connect to a target neuron with the same value modulo 32 go in the same lane. So basically, this first lane will be processing connections going to neuron 0, neuron 32, neuron 64, the next one to neuron 1, neuron 30, 33, etc. So this means that you can have totally zero conflicts in your writing to these lane local memories, and everything can proceed at basically the same throughput as the dense case. And the same approach can be applied to delays. Because the brain is embedded in physical space, so there's delays as spikes travel between neurons, and it's been shown that adding these delays to spiking neural networks can really improve their performance. And this is basically the same problem as the sparse connectivity. We just distribute these kind of delayed versions of the output through the lane local memory, and again, it just turns into a perfectly non-contested write to all these memories from each lane. So we've now talked about what spiking neural networks are. We've talked about the hardware. We've talked about the software. So what have we actually done with this? I'll skip this. We haven't got much time. So first of all, we looked at there'd been some previous results about using stochastic rounding to simulate spiking neurons that seemed very promising. So this is why this has been kind of an integral part of our design. So this is a thing called an ALIF neuron. It's a slightly more complex model. And here you can see the top panel on the left is showing the floating point version. So you can see this neuron is being stimulated with some input, making some spikes, and it pauses, then some more input. But if we zoom in on this and implement it using standard round to zero, you can see that the dotted line, which is the reference, is quickly going away from the the solid line, which is the implementation on the FPGA using 16-bit fixed point, is quickly drifting away from the reference. But if we use stochastic rounding, this stops being the case. You see these kind of standard deviations increasing because we're showing the average across 32 instances of this, but the actual spike times happen at the same time, which is the most important thing, and the difference with the reference becomes very small. So that's stochastic rounding. The other key thing is saturation. So because the inputs that these neurons receive is not really predictable at test time, so you might train your model in some range, but you never really know what will happen at test time. Saturation is very important. So here we see this neuron is being stimulated more beyond the point where the normal version wraps around in standard integer arithmetic. So this is kind of a catastrophic failure, which we don't want. But if we saturate, then we just kind of clip the values. And this is obviously much less catastrophic. So we don't need to be quite so conservative with allocating our fixed point bits, which helps with general precision. So the main kind of applications we've looked at so far are classifiers. So I'm probably going to skip one of these for the sake of time, but the first task we looked at was this thing called the spiking Heidelberg digits, which used high quality recordings of the digits 0 to 9 in English to German, and these were converted into spikes using a kind of model inspired by the brain. And to cut a slightly long story short, the kind of another FPGA accelerator had implemented this model and it got around 73%. But because FEN let us support more flexible connectivity and more complex neurons, we got this up to 80% in our first paper. And then by also adding support for delays, we got this up to 90%, which is getting close to state of the art. So basically, the conclusion here is that by adding support for this kind of more flexible set of neurons, we can get much better actual task accuracy. Okay, there's some other data sets. I'll skip these two, I'm afraid. So future work. The main future work is going multi-core. So like all processors, really the main route to scaling is to add more cores onto your FPGA die. So we've built a dual core version on the Kria, and we're now working to connect these together. And as we said at the beginning, because these neurons are only exchanging sparse spikes rather than continuous activations, this becomes much easier. We only really, on average, you probably need to communicate a spike from a core every 100 clock cycles. So even if you have a lot of cores, you can receive them at a reasonable rate and only transmit slowly. So this is promising, and we're making good progress on this. And the other thing we're interested in particularly is event-based vision. So Prophecy has released a series of event-based cameras. So these cameras, rather than capturing frames, like each pixel sends an independent event stream. So this is really good for this reduces the bandwidth of high frame rate video because you don't need to send all these frames that look much the same. And it's also good in low dynamic light scenarios. So we're building an IP to interface with one of these. So this is one of the things we're really interested in. We're also interested in building a larger accelerator for training. And this is particularly interesting because we've got this event prop training algorithm that gives training the same computational properties as inference. So all the stuff we've done so far can be applied to training, which is really exciting. And I think I don't think anyone's really looked at this before. So that's be done. Another link to the archive here. I'll just stop sharing. And sharing. Am I still sharing?
No, we cannot see. We cannot see this.
Okay. Yes. Any questions?
Folks, any questions or any? So, Mina, would you like to ask a question verbally?
Hi, James. Thank you very much for sharing your interesting work. I have two questions. First of all, do you have any power measurement numbers to share with us? And the second one is how many neurons, what's the maximum number of neurons that you can fit? For example, for that Heidelberg model, how big was the network? Thank you.
Thank you. Both very good questions. So the power measurement is a little bit tricky on FPGA because you've either got the option of measuring like right on the outside as kind of the whole power going into the system on chip, which includes the Mali GPU and the quad-core ARM processor and all this stuff. And then on the other hand, you have kind of power estimation methodologies on the from the FPGA tools. So we've done both, but I think that generally the power usage of the accelerator is somewhere around 1 watt, which is fairly the dynamic power usage of the accelerator is about 1 watt based on the FPGA tools estimate, which is about the same as a lot of other accelerators of the same kind of scale. And in terms of the maximum neurons per core, so that's one of the slides I skipped actually. So you can simulate up to 16,000 neurons per core with sparse connectivity, and that's 200 many millions of connections. So this is you can simulate many more neurons on FEN than you can on any other FPGA accelerator this size that we've seen. And this is because we're doing this, we're using external memory, and we're doing this this streaming that I explained. The actual numbers are in our paper, the most recent FeNN DMA one. There's a figure that shows the throughput and how the simulation time scales with the number of neurons.
Tula, do you want to ask a question verbally?
I think you're muted, Abdullah.
So, Abdullah, are you going to ask a question, or you wrongly raised your hand? So while we wait, any more questions from the chat or from anyone that is willing to ask a question verbally?
No worries.
So it looks like we do not have any new questions here. Okay, so with that, so I'd like to thank you both, James and Zainab, for presenting the work. Is a really dense work, so unfortunately we only had 1 hour for you both to present, but thanks for accepting the invitation. Thanks for starting the first technical session this year. This is going to be recorded, so it should be in our YouTube channel between later today or tomorrow. And then I think I can get your presentation, right, to attach to that. Yeah, and then
yes,
we share with the recording plus the presentation with everyone that have attended today. So again, thank you very much, James. Thank you very much, Zainab. I hope to see you again. In the next technical session, and I believe the next one is scheduled to be for your general awareness in 2-3 weeks from now. Still in the AI context, but I'm going to publish that as soon as I can. Thank you very much, everyone, for joining. Have a great day.
Fantastic. Thank you, everyone, for listening, and Raphael for hosting.
Thank you.
Bye.
Thank you.
Bye-bye.